So these are the basic antiderivative formulas. Okay, basic antiderivative formulas. This one is saying if you want to know, right, the antiderivative some constant. Okay, some constant. Can you see that? Yeah, some constant, right? Does it make sense that if you differentiate like kx, that you will get that constant?
Yeah, because the power of x is 1 and it comes in from...
That's right, right? So if you want to go backward, does it make sense that you will come from this?
Yeah.
Right, that's why it's this. So what's this c about?
A constant?
Yeah, so the thing is, what is the derivative of any constant?
0.
That's right. Okay, so it makes sense that there could be a constant there.
Mm-hmm.
So if you differentiate anything of this form, that you will get k. The constant will disappear. This x will turn into 1.
Mm-hmm.
So if we have k, and I ask you where did that come from, you would have to say this.
Yeah.
Okay.
Okay.
It's the second rule: x to the power of n. X to the power of n.
Mm-hmm.
So you recall that if you differentiate this by power rule, you get this. You subtract 1, you times it by n, right? Like this. This is the power rule. N times x to the power of minus 1. Okay, so how do you go back to this, x to the power of n?
You plus 1 and then n divided by n.
So you would, if you add 1 to that, you will get n, right?
Yeah.
You need to get rid of this n, right?
Yeah.
So what do you have to divide by?
N.
N. But n is 1 bigger than the exponent, right?
Mm-hmm.
So this is how you express that. Okay. So the integration of x to the power of n, the antiderivative of that is you increase this power up here by 1.
Yeah.
Okay, and then you times it by the reciprocal of the power, like this. That's exactly what we did here to get back to x to the power of n.
Yeah.
Of course, you need a constant again, because if you differentiate any constant, it's always 0, right?
Yeah.
Okay. So this is really important one.
Yeah.
This one, did you learn that e to the power of x, if you differentiate that, it stays the same?
No.
Okay. So then now you know.
Oh, okay.
If you don't know,
What's e?
e to the power of x derivative is e to the power of x. So this is like, you know what a 3 to the power of x is. It's an exponential function.
Yeah.
So e is a special number. So I think it's called Euler's constant.
Oh.
Okay, and it's around 2.71, and it has a special application in science. So they named it like, just like we name pi, we don't call it 3.1419. We just call it pi, right? So e is one of those numbers. Yeah,
Okay.
it's one of those special constants. Okay. Okay, so this one here is saying if you have a function, that's a function right there.
Mm-hmm.
So that's a function of x, something dependent purely on x, and if that's multiplied by k, you can leave that k out at the front. So which means you find the antiderivative without the constant multiplied, and then you multiply the k afterwards. So here's an example. Let's say I have the integration of 2x cubed dx, right?
Mm-hmm.
X cubed is using the rule 2. True?
Yeah.
This is multiplied by 2, so we can leave that 2 outside like that. Okay, so what is that?
3. No. Wait. So
You have 2?
derive it, so then you get 1 over 4 x to the power of 4.
That's right. Okay, good. So it's half x to the power of 4 plus c. That's an example of using the fourth property.
Oh.
Okay.
What's the dx mean?
The dx.
Yeah.
So the dx, I think, is something that you don't necessarily have to be so concerned about right now, but it always needs to be there for integral.
Oh, okay.
Okay. But I'm gonna have to go back into really what does integral mean, right? And integral means, let me just tell you a rough idea. It's got something to do with finding area under the curves.
Oh.
Okay, and the way we do that is we cut it up into these approximate rectangles like this. Okay. So this is going into more than what you need to know, but basically this dx represents, so the way we do that is we find the height and we times it by the base. Height times by the base. Height times by the base, right? The dx represents the infinitely small base, and the f at x represents the height. So it comes from a definition of an area. You're probably not going to discuss that in the section where we just talk about antiderivatives. Okay, so right now we're just concerned about how to go backwards.
Yeah.
Just know that it doesn't make any sense if you don't have dx there. It just needs to always be there. Okay. Now for rule, the property 5, if you have a sum or subtraction, you can get the antiderivative separately and then add a result. So for example, if you have 2x cubed minus 3e to the power of x, like that. Okay, again, you always need a dx there. Okay, they will never give you a question with integral symbol without the dx at the end. Okay, so this property is saying we can do this. Okay, we can separate it like that. Okay. Furthermore,
And
if
then
you
take out the 2 and the 3.
exactly, because we can go back to using 4 now, right? Okay, and then we use property 2 and 3, right?
Yeah.
Because this is a power. So what is this?
2 1 over 3 x to the 1 over 4 x to the power 4. Then
Right.
Negative 3 ex. Let's see.
Okay, so do you see? I'm gonna get two constants, c1 and c2. But usually we don't write it like this. If you combine the two constants, what do you get? You get another constant, right? So it's okay for you to write just one constant at the end like that. Okay, so that's it. That's the we just use the property 5, 4, 3, and 2 at the same time. True? Okay.
Yeah.
So yes, that's the antiderivative. And then the last one, this one, at this point, some people some teachers may expect you to know this, some teachers not, right? But did you learn the derivative of ln?
No.
No, right?
No.
Okay. So don't worry about this for now, okay? All right.